TV Studios, it's Tanzu Tuesdays with your hosts, Robert, Burr, and Lee.
All right, we did it. Another successful intro while I'm running the ones and twos, I think. Yes, hello?
Hello. Oh, I'm so proud of you.
You're almost so a professional.
I mean, this is my third time. Third time's a charm, as they say. We've been working on what the output looks like. Apparently that was an issue from last week, Tiffany was saying. So it's all coming together, people. We're professionals here. Act like it.
Do you know how much faith I have in you, Bob?
All of it. All the faith.
I haven't even set up the backup stream in case things go wrong.
Whoa.
No pressure or anything.
Shouldn't tell us that'll jinx everything.
Exactly. Cue Sting. If I ever lose my faith. Anyway. All right. Well, welcome to Tanzu Tuesdays, everybody. Not karaoke Mondays. That's not a thing. And we're very happy to be here. I'm Bob Brinley. With me, as always, Tiffany Jernigan and Paul Charkovsky-Golievsky. Welcome. Thank you for joining us.
Thank you for having us.
Thanks.
And our very special guest, we're so happy to have with us, Emily Casey. Hello, Emily.
Hello, guys. Happy to be here.
We are happy to have you. Where are you coming, broadcasting from?
I'm broadcasting from beautiful Boston, Massachusetts today.
Ooh, delightful. Yeah, I'm in the smoke, like literally outside. It looks like there's fog, but it's not fog. It's just smoke of California. So we are on fire here, and thoughts and prayers, because that seems to be what everybody needs right now.
I keep forgetting that you're in California.
Yeah, yep, I am. And, when you have 11,000 lightning strikes in a 72-hour period, something's bound to light. So anyway, it's very serious. I'm not trying to make light of it. And hopefully all of our firefighter people are actually doing I know they're doing the best they can, but hopefully they're winning, because we were losing for a long time. And then Paul, I know it's hot where you are.
It is hot where I am. Yes, it is. We'll give you our weekly weather update. According to my phone, it is 95 degrees. So it's actually a bit cooler than usual.
Oh, wow. Yeah. Put some pants on already.
Just hope I don't stand up and no one will know.
Oh, right. Yes. I just meant in general, like when you go outside, put some pants on. It's too cold. We've got somebody from Napa joining us. I hope all the fires are not affecting anybody in the Napa area too. We got two big fires going on.
Yeah, maybe you should vacuum your forests every once in a while. You wouldn't have.
Thank you. Yes, it's a note. We'll put that down on paper and see what happens.
Yeah. Now I don't know if you remember, but at the end of last year, start of this year, Australia kind of burnt to the ground in a similar fashion.
Yeah, the whole island continent.
And one of the things they said is when they're looking for like the cause of the fire, there's only 4 possible things that actually start fires.
Okay.
And that is lightning, men, women, and children.
Yep.
So they're your 4 possible causes.
Pretty much nails it. But in Australia, I just learned they're not called firehawks, they're called firehawks. And what they've learned is to flush animals out of an area so that they can hunt them. They'll take like a twig or something that's on fire and put it in another area. And so they'll spread the fire as a way of getting
actual
food for
hawks
them.
Will spread the fire.
They're called firehawks because
that's crazy.
Fire. Right? Like yet again, another reason why Australia is just always trying to kill you. So anyway, well, good. I'm glad everybody's here. Thank you so much for joining it. And like I said, we have Emily Casey. Emily, we want to talk a little bit about you, get to know a bit more about you. Excuse me. So, kind of, a quick little blurb on who you are in this dev kind of Opsian world that we live in, and kind of what got you started.
Yeah, sure thing. My focus for the last couple of years has been on Cloud Native Buildpacks, which I'm going to be talking about today, which is
coincidentally.
Yes, of course. It's a CNCF project that we started at Pivotal before joining VMware in collaboration with folks at Heroku. It's the next generation of Buildpacks. which anyone who's familiar with Cloud Foundry or Heroku platforms would be familiar with the older version of Buildpacks. I ended up in this space through a circuitous route. Started in software consulting at ThoughtWorks, and then came to Pivotal, and then wanted to get into Cloud Foundry, and then found my niche area here that I'm very passionate about.
Well, that's wonderful and great. And you're in Boston, but you live in the New York area generally. Do you have any animals there?
I do. I have a cat.
Oh, you're a cat person. Wonderful. Paul also is a cat person.
I'm not a cat person, only because I start sneezing.
Yeah.
Trying to convince him that he wants to make Zoom cameos, but he's not convinced yet.
Oh, yeah. Yeah.
Yeah, we have two cats, and I like them, but they don't like me all that much. So
oh no,
it's a one-way thing.
I feel like that's
why I have to
the most.
That's why I have the pet
cat thing ever. Yeah, that's right.
They like me back.
And it's true. That's right.
I want a trash panda.
You've also got skunks. I get threatened by a skunk on most of my evening walks. To include last night, or 2 nights ago. I heard something. It was really dark, and I put my flashlight, and it was a skunk leaving with tail high up. And I was like, I know you from before. I've seen you. So yeah, I think it's just a matter of time, and I'm going to have to start stocking up on tomato soup.
Right. So when they're quite young, they haven't developed the scent gland, so you don't have to worry about it when they're like tiny little babies. But when they get mad, they stomp at you. They stomp their 2 front feet at you. It's super cute.
I've definitely watched YouTube videos of a bunch of baby skunks in a tub stomping.
Oh my gosh. I'm gonna look up these firehawks and baby skunks after this.
Yeah, the opposite effect is happening.
And I discovered that skunks also enjoy eating mini marshmallows.
You just
which I'm sure
that?
is a very, very bad thing.
Definitely.
Oh, did you discover that?
It is.
Yeah, because marshmallows are found naturally in the wild. So, you have a marshmallow bush,
right.
and they were feasting on it. Yeah, that makes sense.
Exactly what happened.
It's like when Doritos came out with the organic nacho chip. You're like, are there really just organic chips growing out on a tree somewhere? I don't think so. Thanks. You're not going to pull that one past me. But anyway, well, great. And then where are you originally from? Are you from New York City, New York State, or where are you originally from?
I'm actually originally from the Boston area. So I'm just here for a couple months now, but this is my hometown.
Oh, nice. Okay. So then there's that big Boston-New York rivalry. So was it a big deal to move to go Babe Ruth and go down to New York?
I took a detour through Chicago. I was in Chicago through 10 years. I feel like that's actually the city I'm most loyal to. So I've just kind of sidestepped the whole thing.
Love me some Chicago. Chicago's a great town. For a couple of months of the year. And then you can have it. You can.
I feel like the suffering in the winter is important so that you fully enjoy the summer. No one loves summer like Chicago.
Right. You got to Seattle is
it's 70 and sunny with the cool breeze tonight. It's glorious.
Yeah. Seattle also. It's not the bitter cold that Chicago has, the polar vortex, type of stuff, but you just get pounded with rain. Yeah, it's
not
wet.
Pounded. It's worse in Georgia. There's more rain, but it's just more days of drizzly or just rain in general.
Got it. All right. Well, there we go. Well, I think we've done a good job of getting to know you a little bit, Emily. We're, like I said, very happy to have you here. So I don't want to take any more of your precious time. And let's.
Well, did you mention? Re-mention?
Oh no, I'm sorry. I'm sorry. We have to do our kind of
quick. Chop.
Okay, because this is happening next week. Everybody, Spring 1, the big virtual conference that normally it's a conference in person, but it's virtual this year. Spring1.io. We have our schedules out. We have our tracks. I will be personally emceeing Beginner Friendly Spring. Me and Cora Iberclyde, who has been a previous presenter on this show, we will be emceeing that. Paul and Tiffany, which one are you presenting on? Cloud Native Platforms?
Yes.
Cloud Native Platforms. So yeah, go to spring1.io, an amazing website. It has all the schedule, like I said, all the different tracks. Check it out. Social tracks even, where you can just mess around and go check out yoga. It's also got workshops galore. Get up to date on your spring. What else? Let me just...
And on Tuesday, next Tuesday for Tanzu Tuesdays, we're going to be talking with our awesome Mother of Dragons, Mama Bear, Tasha, about Spring 1.
That's right. We're going to be doing our big Spring 1 preview next week, so make sure you tune into that. We had Spring 1 tour last week, so tune in next month where we're going to be doing a breakdown of our Spring 1 kind of conference. We're going to be talking about the highlights. So that'll be a lot of fun. Spring1tour.io next month. And then VMworld is the end of September 29th through October 1st. Our very own Paul Charkovsky-Golievsky will be presenting along with 599 other people, I think. Not to lessen, but it's just a huge conference. There's so much stuff to learn about. So definitely check that out at vmworld.com. Anything else I've missed, my friends?
Well, Tiffany is speaking at Spring 1 next week, right? So what time and day are you on, Tiffany? Do you know?
I'm on the I'm on the second day, so that's the 3rd, and my time is I think at 2 p.m. Eastern.
Cool,
excellent. So check
you
all of that out.
You should all tune in for that.
Oh, and Spencer,
Emily,
who's been on our show,
do you have,
are you going to be in it?
I'm actually emceeing one of the tracks. I think it's called Intermediate Spring.
Well, good. That'll be there's beginner spring and then intermediate to advanced spring. So that's awesome. Yeah, we're just pumped. There's gonna be so much content. Go check it out, everyone. Spring1.io. All right, thank you for reminding me, Tiffany. And now we're done with our word from our sponsors. On to you, Emily Casey.
All right, let me share my screen here. Okay, everyone. Welcome to Building Better Images. My name is Emily Casey, and I'm going to be talking about Cloud Native Buildpacks and Paketo today, which is a set of Buildpack implementations. So who am I and why am I qualified to talk about this? I'm Emily Casey. I've been working on the Cloud Native Buildpacks project for a couple years now. I'm a core team member on the CNCF project. You can find me on GitHub at ekcasey. I also have a Twitter. I've literally never tweeted, but someday I might. So if you follow me, you could be there for my very first tweet. On GitHub, you might recognize me as this wonderful monocled cat here. So what is Cloud Native Buildpacks, also known as Buildpacks.io? Buildpacks.io is a CNCF project that provides tooling that turns source code into images. So at a very high level, you are a developer, you have some source, you want a Docker image so you can run on a variety of platforms. How do you get from your source code to your image? Cloud Native Buildpacks provides one solution, one of several solutions to this problem. If you look in this Docker image diagram over here, you can see that a Docker image is made of layers. And we're going to talk about different types of layers today. We're going to use the phrase stack image layer to describe operating system, layers that contain an operating system or operating system level dependencies. Dependency layers to describe layers that contain dependencies of your app layers to describe layers that contain your app itself, and there are other runtime layers like for a language runtime. So let's back up a second. I just said that Cloud Native Buildpacks turns application source into Docker images, but what exactly is a Docker image? I know most of you are familiar with this, but it's nice to start from a place of shared understanding. So a Docker image is an immutable artifact containing the operating system, file system, the application file system, a command, and a command to start the application. So it's an entire runnable unit that contains all of these pieces. It is a self-contained environment, which means that it runs the same anywhere. And this differentiates it from how applications were commonly run in the past, where you installed your application artifact into an environment that already existed and ran it there. So what you were deploying was your application, maybe doing some steps in advance, either manual or automated steps in advance to set up the environment for your application to run. Now you can, as a deployable unit, deploy the application and the entire environment that the application runs in. So this has been the big innovation that have made Docker images sort of take over DevOps. So most people when they think of Docker images, they think of Dockerfiles. They think of these things sort of as synonymous, that the only way you can get a Docker image is by writing a Docker file. And Dockerfiles are by far the most common way to create a Docker image. They're so ubiquitous because they're very flexible and straightforward. You can run any command and you can mutate any file. And this is a very powerful tool. The fact that it's so flexible, though, opens up several weaknesses. It's very hard to write Docker files, to keep Docker images built from Docker files up to date, because all of the layers in the Docker image can contain any random diff that came from a command in your Docker file. There isn't the layers aren't content aware, and therefore, if you're presented with any given Docker image, it's hard to know which layers need to be updated to patch a CVE. Creating Docker files across an organization to deploy many applications often involves a lot of copy-paste. And even if your organization does this well, like say has a shared base image for a certain language ecosystem, it can be hard to keep the images and Docker files produced consistent. These things can drift over time as best practices in the organization change. And finally, to create a Docker file that doesn't have build dependencies in the final image, which creates unnecessary surface area for vulnerabilities, to create a Docker file that doesn't need to be rebuilt frequently, it takes a lot of effort and know-how. So getting started with a Docker file is very simple, but writing a good Docker file can actually be a challenging task. So backing up here for a second, in the original version of Cloud Foundry, containers on the platform were created in a different way, not using Docker files. Instead, they used a technology called Buildpacks, which was originally invented by Heroku in 2011. And what Buildpacks did was, instead of creating an image, they created a different immutable artifact called a droplet or slug. And this immutable artifact contained the application file system and the command to start the application. What made it different from an image is it didn't contain the operating system and operating system level dependencies. At runtime, an image called the rootfs was used to create a container, and that contained the operating system dependencies, and the droplet was streamed into the container to create the final running state. The advantage to this was that it was easy to update operating system level dependencies for the entire platform without having to rebuild the artifacts, the droplets or slugs. Also, the interface for Buildpacks didn't require the same sort of knowledge that the interface that a Dockerfile requires. So application developers could just CF push their application without having to know exactly how to build it into an image. And they got consistent secure and easily updatable images without having to create a Docker file. The downside of this is that it wasn't using the OCI standard. At a certain point, the image was abstracted from the end user in Cloud Foundry. But as we move towards new platforms like Kubernetes, and as we try to make our technology more flexible and modular, we would like to embrace the OCI standard and create portable image artifacts so we can be part of a broader ecosystem. And that's where Cloud Native Buildpacks comes into the picture. So Cloud Native Buildpacks takes some of the advantages of the original Buildpacks and brings them to the Docker image world. So we want Docker images, we love Docker images, but can we get a Docker image without a Docker file? The answer to that is Cloud Native Buildpacks, which replays the original Buildpack model on top of the OCI standard. So it brings that model to the OCI world. And it has some additional advantages compared to Dockerfile. It has faster builds. It has reusable layers. So you can reuse layers across versions of an app and even between apps. The images are reproducible, both at the entire image layer. So identical inputs should produce an identical image output, and at the layer level, which allows individual layers to be reused. Because we've created this ecosystem around a specification rather than around a single tool, the specification boundaries have been designed to make the ecosystem very modular and composable. So people should be able to use the platform, use the standards to create a variety of platforms and a variety of build packs and plug and play with the existing tools. So you might ask, are there other tools that do similar things? The answer is yes. But a lot of them are either limited to a particular language ecosystem or don't provide all of the same advantages as Cloud Native Buildpacks. I'm actually going to be doing something a little bit different with this talk today compared to talks I normally do, where I focus on the how of Cloud Native Buildpacks. There was recently a talk about building container images on the show, actually, which did a good job of demonstrating some of the basics of how to do a pack build. So instead of rehashing some of those basics, I'm going to focus on the whys of Cloud Native Buildpacks, like what decisions we made when architecting the Cloud Native Buildpacks that we think produces an ecosystem that's advantageous compared to the other available tools. I'm going to focus on the whys. I'm going to hit on a lot of the points that are on this checklist that I cribbed directly from the Buildpacks.io website, but try to organize them into higher level themes. So that's our big plan for today. But before we can dive into the higher level themes, I need to introduce you to some concepts that we'll be talking about and referencing throughout the talk. So before, when I said Cloud Native Buildpacks takes source code and turns it into an app image, that was, as you might have guessed, a bit simplified. There are several inputs that are required to create the app image beyond just source code. So you need the build packs themselves, which are reusable components of build logic that together can be used to create a full build. You need the lifecycle, which is a shareable component of Cloud Native Buildpacks that we're going to discuss more in a second. You need a build image, which is the environment the build actually runs in. And then you need a run image, which is the base image for your generated app image. Now that might sound like a lot of inputs that you need, but luckily all of those inputs, except for your source code, can be packaged into a convenient bundle called a builder image. So most platforms accept source code and a builder image and use it to produce an app image. So let's talk about how exactly this happens and focus on modularity as we talk about this. So Cloud Native Buildpacks is a specification project. And the specification at its heart defines two APIs, the Platform API and the Buildpack API. So a platform is a tool that users can interact with in order to, a platform provides an experience to users where they can supply a source and receive an image. Buildpacks, on the other hand, are pieces of build logic that can be contributed by different vendors or open source projects. The Cloud Native Buildpack project itself actually doesn't provide any build packs. It provides a specification for how a person could create a build pack. And then the lifecycle is the component that sits in the middle and mediates the interactions between the platform and the build packs in order to produce an image in a consistent manner. So a platform is responsible for invoking the lifecycle, which is in turn is responsible for invoking build packs in order to generate an image. And what's nice about this is that folks can focus on just the piece of the ecosystem that they would like to modify or contribute to. So if a vendor, say, wanted to create a new build platform, they wouldn't have to, they just need to learn about the platform API and invoke the lifecycle, which in turn can deal with the nitty-gritty of invoking build packs and turning those into images. On the flip side, if someone just wanted to extend the build with a tiny piece of build logic, they can implement a build pack that adheres to the Buildpack API and without having to worry about a platform or how that build pack fits into the broader set of build packs. As long as they implement the Buildpack API, they can slot their build logic into a build. So there are many examples of tools that implement the platform API. One of them is Pack, which is a CLI tool that's actually provided by the Cloud Native Buildpacks project itself. But there are more. There's Kpack, which is a Kubernetes-based open source tool developed by VMware. Spring Boot actually implements the platform API to provide a Maven plugin that builds Spring images. Tanzu build service is sort of like Kpack++. So it's a distribution of Kpack that comes with proprietary build packs and an air-gapped install experience and all of the things that enterprises need to use Kpack seamlessly. We've already talked about Heroku, which I think many of you are probably familiar with. There are also CI/CD tools that have implemented the platform API in order to provide a platform-like experience that integrates into existing CI/CD pipelines. So Tecton and the Circle CI orb are examples of this. And finally, Google App Engine provides another example of a platform. So all of these tools use the lifecycle that's provided by the Cloud Native Buildpacks project and interacts with it using the platform API in order to produce a user experience built on top of Buildpacks, but one that's tailored for their specific audience and use cases. So let's talk about how this specification enables an ecosystem to flourish, an ecosystem of platforms, compared to other tools that provide a single tool, like something like Co or Jib, that's usually run as a single CLI tool. Instead of doing that, the platform API allows an entire ecosystem of tools to flourish. So the Pack CLI, it provides a command line UX. It uses Docker to run the containers. So the lifecycle is generally orchestrated by running a series of containers. We talked about builder images before. Those containers are frequently created from a builder image. and the lifecycle is invoked in those containers. It uses an imperative model, and it's really designed to be lightweight. So it's very easy to install. It's very easy to get started. Users can iterate quickly on a few images. You just need to brew install pack, select a builder image, pack build, and you're off to the races. So this is a great way for people to try out the Cloud Native Buildpack experience without a lot of overhead, and is great for folks who want to iterate on a build pack or iterate on an application in a local, fast manner. Spring Boot provides Maven and Gradle plugins that have some of the same advantages of the Pack CLI in terms of being able to, it's similar in that it uses Docker as a container runtime. It follows an imperative model. And you can use it to iterate quickly locally on your application or run in CI. What differentiates this from Pack is because it's built into Maven and Gradle tooling, it is embedded in an existing toolchain that Java developers are familiar with. It can also be appropriately opinionated. So unlike Pack, which requires you to select a builder image or select build packs, the Spring Boot plugin has default opinions about what build packs produce the best Spring images. CI/CD integrations, we talked about a little bit before at the top. An example here would be Concourse, Tekton, GitHub Actions. We also provide a Circle CI integration. These frequently run in Docker, but it can depend on the CI/CD tool. Tekton, for example, uses K8s to schedule container. And the benefits of these platforms are that they integrate seamlessly into existing pipelines. So you can just use one of these integrations to drop a Cloud Native Buildpacks build into an existing pipeline. So now let's get into the K8s runtime examples. So Kpack is optimized for a Kubernetes experience. Rather than providing exclusively a CLI interface, although it does provide a CLI interface, folks can interact with Kpack using Kubernetes custom resources. The containers that run the lifecycle, rather than being scheduled in Docker or scheduled in Kubernetes, the biggest difference, in my opinion, is that it follows a declarative model rather than an imperative model. So rather than telling it when to build a new application, like all things in Kubernetes, the custom controllers provided by Kpack will constantly be monitoring the desired state provided by the user and the actual state, and scheduling a build to bring the actual state in line with the desired state whenever that's necessary. The big benefit of this is that it makes it very easy to keep many images always up to date and to manage that centrally. So over here on the left, I have an example of an image config, and it's pointing at a builder image, which we said before contained build packs and references to stack images. So for example, if I pushed a new version of my builder that contained an updated Java build pack that installed a newer version of the JRE, maybe one containing a patched version because there was a CVE fix. Because my image has declared that it should be up to date with the sample builder, the Kpack controller will see that a build pack that I've used has changed and schedule a build to bring my image into compliance with the requested state. This also works for things like stack images, for example. So if I pushed a new version of the run image, which, as we said before, was the base image for the generated app image. So we basically push a new base image, Kpack is going to go and take all of my apps that use that base image, which could be thousands, and update them all automatically for me. So this can give you a lot of confidence that all of the images in your ecosystem are at latest and don't have security vulnerabilities. Tanzu build service, we said before, was a distribution of Kpack with additional features. So it has all of the benefits of Kpack, but it also provides benefits that are particularly important to enterprises. So it can be installed offline, and it ships with a comprehensive set of build packs that enable a wide variety of enterprise integrations. So all of these platforms, if they because they're all following the specification and using the same lifecycle, if you provide them with the same inputs, you're going to get the exact same image digest out. And that's what makes this model so powerful. So folks can decide what the correct experience is for them, whether they're using the Pack CLI to debug something, whether they're using Tanzu build service to monitor 1,000 Java apps for their entire organization. You can choose the platform based on the UX that is right for your use case and get the exact same results out the other side. And that allows these things to even be used in combination. So let's say in production, I want my images always up to date. So I'm using Tanzu build service to declaratively specify what I want my images to look like, and it's continually updating them as CVE patches come out. I can use Pack locally to develop my app or to try out a new Buildpack integration that I would like to add to my build service. And because I get the same results from using Pack build that I would get from using the Tanzu build service, so long as I put the same inputs in, these can be used in combination in a really powerful way. So on the other side here, we have the Buildpack API. Buildpacks provide pieces of logic that contribute to the final built app image. So an example might be a Buildpack that installs the JRE, might be a Buildpack that compiles your application, or a Buildpack that installs a specific APM agent. And there are a couple well-known sets of Buildpacks. We're going to focus, most of our examples today are going to use Paketo Buildpacks. So Paketo is an open source project that contains Cloud Native Buildpacks that are the next generation of Buildpacks coming from the Cloud Foundry Buildpacks. So they're the descendant of the Cloud Foundry Buildpacks. That has now moved into its own project. Tanzu Buildpacks contain distributions of the Paketo Buildpacks, including offline package ones and also additional integrations that are important for enterprise users. Heroku provides a large set of Buildpacks. Google provides a comprehensive set of Buildpacks. And it's very easy as a user, if you can't find a Buildpack from any of these Buildpack vendors, to bring your own Buildpack. And because of the Buildpack API, if you want to modify the build, you can bring a Buildpack that does one piece of the build logic and still use it in tandem with Buildpacks from a vendor. So you don't need to take responsibility for the entire build to bring a piece of custom logic to the build. So first, let's talk about Paketo. Paketo is open source. It's community-centric. It's everything you need to get started with the most popular languages and frameworks. You can find all these build packs at github.com, Paketo Buildpacks. They are updated in a timely manner. So what's nice about getting a build pack from a build pack provider like Paketo is that a lot of the dependencies installed by a build pack can have CVEs, just like any piece of software can. And full-time Buildpack providers that have teams focusing on this full-time will produce new versions of the Buildpacks within a certain time frame whenever a CVE comes out. It's one of the big advantages of using an ecosystem of Buildpacks like Paketo rather than hand-rolling them all. Tanzu Buildpacks are proprietary Buildpacks. It includes a superset of the Paketo Buildpacks and additional Buildpacks that are tailored to enterprise environments. So the Tanzu Buildpacks have the same benefits as the Paketo Buildpacks because it includes all of the Paketo functionality under its umbrella, but it provides different packaging of the Paketo Buildpacks. They can work in totally air-gapped environments without connection to the internet, and it works with popular APM and security tools. And also, of course, comes with a support package. So this takes the raw tools that Paketo offers, sort of the Buildpacks for a variety of language ecosystems, and then adds all of the niceties and integrations that you would need to run this in an enterprise. Finally, you can bring your own Buildpack. So it's pretty simple. If you're writing a simple Buildpack is simple. Many users will write a simple bash script to contribute one-off change to the build. You can see the one on the left is a bit contrived, but it's providing a process to the build, and it's doing some debugging work by echoing the contents of the working directory. So if you want to make a change to the build and no Buildpack provides the change of the functionality you want, you can write a custom Buildpack and implement exactly what you need. And you can provide just the change you want without re-implementing everything. So this can either be an additive change or it can be a replacement. For example, if you had a set of Buildpacks you liked, but you wanted to use a different distribution of one of the dependencies that it was installing, you could replace just that one module in the build with one that installed your particular distribution of the dependency and not change anything else. So it's very easy to plug in a small diff to the build logic. So finally, the way Buildpacks are distributed allows you to find the right level of granularity when you're building a Buildpack or deciding which Buildpacks to run. So higher level Buildpacks can be composed of several lower level Buildpacks, which allows you to learn progressively about the complexity that's captured in a build. So for example, if I want to build a Go app and I want to do it with Paketo, I can use the Paketo Go Buildpack right here. And the Paketo Go Buildpack. And if I don't want to change anything that's being provided by this high-level Buildpack, that's all I need to know. I know I want Paketo Buildpacks, and I know I'm building a Go application. But actually contained within that Go Buildpack are several smaller modules. So there's the Go Build module. There's a Buildpack that deals with vendor modules. There's a Buildpack that deals with dep dependencies. So you can, in these tiny pieces together, make up what it means to build an application for Go. So Go dist would install Go itself. Go build uses Go to build your application. And then the other Buildpacks provide a variety of dependency solutions. So if I was using a dependency solution that wasn't included here, I might then say, okay, knowing that I want to run Go isn't sufficient for me because the Paketo Go Buildpack doesn't include Glide or whatever dependency tool I want to use, but I don't want to rewrite everything about what it means. I don't want to have to know everything about how to install Go and how to build. So instead of replacing the Go build pack, I'm going to take the pieces I want, like Go dist and Go build, and then simply just replace the build pack that installs a dependency with the one that installs dependencies using my preferred solution. So the APIs here provide another advantage, which is upgrades. So because we have two distinct APIs that don't depend on each other, different components in the ecosystem can upgrade at different times without affecting each other. So if the lifecycle supports 3 different versions of the platform API and 2 different versions of the Buildpack API, any given platform can choose which version of the API it would like to use when interacting with the lifecycle. The same is true for build packs, even build packs within a build. So multiple build packs that are contributing together to a single build can use different versions of the Buildpack API. And this allows different components to decide how and when to upgrade in a way that doesn't affect other components in the ecosystem. So we've talked a bit about modularity and how the specification and the design of the APIs has sort of allowed an ecosystem to develop out of Cloud Native Buildpacks rather than just a single tool to be shipped from the project. The next big benefit of the ecosystem is transparency. So the metadata that we attach to builds and sort of how we have specified that to allow for countless integrations, both by platforms and by build packs. So a lot of times when you have a Docker image, unless someone has thoughtfully provided an entire history of the image, it's hard to know exactly what's in that image without opening up the box. What we believe in Cloud Native Buildpacks is that everything you need to know about the image should be provided in labels on the image itself, so that you don't need to do the labor-intensive, data transfer-intensive operation of downloading and running the entire image to see what's inside. So in some ways, we want our images to be like this box with a barcode on it. So you should be able to just look at the image config, which is small and cheap to download, and from that be able to figure out everything that's inside the package without having to open the package up itself. So labels are added to an image progressively by different components of the system as the build goes through the process. So stack images, which we said were the base build image and the base image that we use to create the final app image, already come with labels on them that describe features of those images. When a platform invokes the lifecycle, it can provide additional metadata, which you can see here in the IO Buildpacks project metadata. So the platform is the one providing the lifecycle with the source code. So it knows where the source code came from, and it can provide this metadata at the time that it invokes the lifecycle. The lifecycle itself is going to add metadata to the image that describes how it was built and the layers in particular that were added to the image. And finally, build packs themselves can add arbitrary labels to the final image. So you might notice that a lot of these labels start with IO Buildpacks. IO Buildpacks labels are labels that are specified by the project and therefore can be relied upon across a variety of platforms and build packs to produce certain types of data in a standard format. And this specification allows for a lot of creativity in designing interactions around it, because you can trust that any given build pack, no matter whether it's from any given build pack, whether it's from Google or from VMware, is providing its data in a certain fashion. Same with platforms and lifecycles. The labels that don't begin with IO build packs are arbitrary Buildpack-Provided labels. So any contract built on top of that would be a contract that is aware of the specific build packs that are running and what data they are going to be putting into particular labels. So starting with stack metadata, this is the full set of labels that we believe can be added to a stack image, or are specified that can be added to a stack image. The first two, which you see in this example, where I've inspected an image built with Cloud Native Buildpacks and looked at the full set of labels. These are the two required stack labels. One describes the stack ID, which tells you whether you can use a given image as a base image in this ecosystem. So a build image with one stack ID must be paired with a run image with the same stack ID. And later when we get into rebasing, you have to rebase. You can only rebase on an image with a matching stack ID. The same is true for mixins. Mixins identify information about the stack. What a mixin describes a particular delta on top of a base stack image. What a mixin name means is contextual to a given stack ID, but in most of the examples, which are using the Bionic stack ID, mixins directly represent Debian packages that have been installed on the image. Additional metadata about the stack can provide a homepage for the stack, can provide a name of the distro and version, can version the stack images, and provide more information about when it was released, what it's intended for, and IO Buildpack stack metadata is a catch-all for any data the stack author might want to provide to downstream consumers. Next, we're going to get into the platform-provided metadata in the IO Buildpack's project metadata label. Right now, that only includes source metadata, so it describes the source that was provided to the lifecycle when the platform orchestrated the build. Includes the source type, so an example of that would be Git, and data about the source. So an example of that would be like the commit SHA or the repository. And because the platform is responsible for invoking the lifecycle and providing it the source, it's the platform's responsibility to describe where it got that source from and provide it to the lifecycle, where it's then added as a layer to the image. The lifecycle itself will add two labels. So IO Buildpacks build metadata and IO Buildpacks lifecycle metadata. The build metadata contains the build packs that were used to create the image. It contains processes that were provided by the build packs. So these are processes you can launch when launching an image. It contains a launcher version. So the launcher is actually a component of the lifecycle itself that's used when the image is run to kick off one of the Buildpack-provided processes. It also contains a bill of materials. We're going to discuss this in depth, so hold your horses on that one. Finally, lifecycle metadata in the IO Buildpacks lifecycle label describes all of the layers in the generated image. So it maps different layer SHAs to different domain concepts. So it'll tell you which layers contain the app, which layers were provided by different build packs. These are named layers. It'll tell you which layer contains the launcher, and it can also provide metadata about each of those layers, which can be used during a rebuild, as we'll get to later. So when we were discussing the build metadata label, I mentioned that it also contained a bill of materials. This is one of the most important pieces of metadata that we stick on an image. So it's different entries in the bill of materials are generated by different build packs that contribute to the build. And the sum total of those entries is put together to make the bill of materials. One question that comes up is this isn't generated automatically by the lifecycle. The quality and completeness of the bill of materials is going to depend on the build packs themselves. But if you're getting your build packs from a trusted source, then the bill of materials can become a trusted and informative piece of data that's available on every image that you build with Cloud Native Buildpacks. So here's an example entry describing the JRE that was produced by the Paketo Buildpacks Belsoft Liberica Buildpack. In addition to saying that it added a JRE to this image, it contains very useful information like what the license for that JRE was, what is the name of the JRE, what URI was this dependency originally fetched from, what is the version of the JRE. And you can see how having this sort of data about every single thing that is installed into your application can be a very powerful tool in the end. So you can develop license scanning tools that go through and read the licenses out of every entry in the bill of materials. There's never a question about where a particular file in the image came from because you can check the bill of materials and find the URI. So if build packs use this to their advantage, this can be a very powerful tool for end users. Finally, Buildpack-Provided labels. So build packs can provide any arbitrary label as long as it's not starting with IO build packs, which we don't recommend. And this can contain information that can be used to create higher level experiences in a platform. So for example, the Paketo Spring Boot build pack adds org framework boot version to every image that contains Spring Boot. And this allows you to do things like if I have 1,000 applications in my organization and I want to know which ones are on an outdated version of Spring Boot, without actually downloading or starting any of these images, I can just query this label on all of the images and get this one piece of data I want. So specific build packs can provide labels that allow for really powerful integrations. We don't just apply this philosophy to the app image, although that's probably the most important place because that's the artifact that end users can be deploying to prod and they're going to care about very deeply. But builder images, which if you remember contain the set of inputs needed to run a build, also have a label where we specify everything we put in them. So all of the build packs themselves, links to all of the build packs, the order build packs will run in, who created the builder. So in this example here, you can see it was Pack CLI version 0.13.1 created this builder. Also what version of the lifecycle is contained in that builder and what APIs that lifecycle supports. So for example, if I wanted to build with an extra build pack that I wrote, it'd be helpful for me to know which build pack APIs I'm allowed to use. And finally, the stack ID identifies what line the run images are from, what line the stack images are from. And run images provide references to images that can be used as the base image when building an app image. So that was a lot of labels. We learned a lot about what's in our image. Now that we know what's in there, the question becomes, is what's in there the right thing? Which is an area where Cloud Native Buildpacks provides a lot of peace of mind to end users. I would say security is one of the major reasons that people are drawn to adopt this tool. So let's talk about why. So vulnerability in images is a big problem. People go on Docker Hub, they pull down popular images. This report from SNCC in 2019 pointed out that the top 10 most popular Docker images each contain at least 30 vulnerabilities. That is terrifying. And these vulnerabilities, well, people don't know that they exist. The work that it would take to fix them is minimal at times because most of these images, 44%, could be fixed just by swapping the base image. So the vulnerabilities aren't even in the tools that were installed on top of the base image. So how does that relate to Cloud Native Buildpacks? So let's tell a story about a CVE in OpenSSL. So imagine I have an image that contains a Node.js app. It has a couple layers. It's built from a base image that contains OS packages. I installed Node.js on this image, and I install my Node app on top of that. And you can see what some of that, like a skeleton of what a Dockerfile to create that might look like. Now, imagine there is a CVE in OpenSSL. My image is vulnerable, which is already a problem. But now if I have, say, 500 Node.js apps, which is an easy thing for a large organization to accomplish, not only is that one Node.js image vulnerable, when the CVE hits every single Node.js image in my organization, and images built on top of other languages are vulnerable. So this is a big problem for my organization because I need to patch all of these images so that I can help my security team protect my customer data and do the right thing. So let's talk about how these images came into being. If my organization uses Dockerfiles and they use Dockerfiles, what I'm going to call the wrong way, each of these images is a snowflake. So they're managed by individual teams coming from a variety of base images. They have a variety of different node installations before the app is on top. So each one of these images is a pet of the team that created it. How long does it take me to patch all of these images? A long time, right? If you think about it realistically, months is optimistic. It could take years to patch all of these images. You need to reach out to each team that creates one of these images. Some of these might not be actively worked on a regular basis. They need to update their base image and they need to rebuild. This image needs to run through CI. It needs to be installed to prod. It needs to pass a bunch of checks along the way. If you're lucky, they can rebuild on top of the old app code, but it might be hard for them to get the app code that's deployed in prod through a build and deployed. They might just wait for the next release, which could take who knows how long. It takes a really long time in the worst case scenario, but if I'm using Dockerfiles, even the best case scenario can take a long time. So imagine I have an organization where everyone is using the same base image. Then an operations team has created a Node image that installs a particular version of Node on top of the blessed base image. And all teams that are creating Node.js apps then use this Node image. So this situation is better, but it still might take some time for all of these dev teams to pull in the new corporate Node image, rebuild, retest, redeploy. To turn over an entire large organization is going to take time. And your organization is going to be vulnerable during that time. So Cloud Native Buildpacks provides a unique feature called Rebase. this is distinct from a build in that the application and dependency layers aren't being recreated in this situation. All it's doing is taking an app image that existed previously. You can imagine this being like our corporate node image that had a vulnerability in the bottom. And it replaces the base image layers with the layers from a newer patch base image. So the reason this works is due to something called ABI compatibility. The long version of that is application binary interface compatibility. So operating system vendors like Canonical for Ubuntu guarantee a certain type of compatibility when patching, which means that a binary compiled on top of one version of Ubuntu Bionic is guaranteed to run identically on top of a patch version of Bionic. So now if I am using a C&B managed image to rebuild my app, I create a new run image that has the patch version of OpenSSL in it. And all I do is run rebase, and my existing layers, because this is ABI compatible, can be a new manifest can be generated that uses my existing application and node layers and just replaces the base layers with the new uploaded layers. And this doesn't require me to recompile or rerun anything. It's a very fast operation. All I'm doing is creating a new manifest in my image registry that contains this new set of layers. And because of ABI compatibility, I can trust that this will run and function exactly the same as the previous image, minus the vulnerability, of course. And this is so trustworthy. This is what underpinned the droplet and rootfs upgrade model in Cloud Foundry. And for years, we were trusting ABI compatibility to rebase droplets on top of new OS images and directly run them in prod and never ran into any issues. So now with Cloud Native Buildpacks, we can take that model that worked in Cloud Foundry and access the same advantages, but using OCI images. So now back to my scary 500 app situation. If I'm using this rebase, and imagine I'm using it with Kpack. So all I had to do was upload a new version, a new image with the upgraded OS level dependencies, so the upgraded version of OpenSSL. Now all of a sudden, Kpack, which declaratively keeps all of my images up to date, is going to rebase each and every one of my images. And then hopefully another part of my ecosystem is going to redeploy it. So this becomes, the ETA to mitigation is a few minutes, maybe even faster, which is crazy thinking that in our original example, it was going to take us years to perform this upgrade. So finally, one of the major benefits of Cloud Native Buildpacks is efficiency. We try to make builds as fast as possible, minimize data transfer, and minimize unnecessary storage space. So let's take a minute to look at what happens in a traditional Dockerfile build. Imagine that I've written this Dockerfile to build my application, and harkening back to our base image update example, I was told that there was a vulnerability in Ubuntu Bionic, and I'd like to rebuild this and get a new version out. Once I've replaced the base layer that my application is built from, every directive in this entire Dockerfile needs to run again. So this can result in a lot of slow and unnecessary work. For example, if my application hasn't changed or a JRE that I've installed hasn't changed, I still need to run through all of the steps that downloaded and exploded that JRE. I might need to recompile my application depending on whether I'm compiling from source in my Dockerfile. And the further up the chain of commands, the change has occurred, the more work needs to be done to generate a new image. Now let's look at how this works in Cloud Native Buildpacks. So layers are independently reusable, and this can be true because they're disjoint. The way the Buildpack API works is that Buildpacks contribute net new dependencies to individual directories, individual named directories that are turned into layers, or they contribute to the application directory, which is turned into layers in a prescribed manner. And this means that no two layers are going to edit the same file. And what that means is that if an earlier layer in my stack has changed, I don't need to run through the build process to see if the difference that would be applied to a file in that layer by a later layer changes or not. I know that because of this disjoint, it doesn't matter to me at all. So you can see this output is coming from a pack build. And in this build, we originally installed with OpenJDK 11. And now I've switched to an older version. Sorry, not OpenJDK, Belsoft Liberica. But the version was 11, now we've switched to 8. And what you can see is that things that don't need to change have this beautiful green reusing sign. So Buildpack can look at the metadata and say, I know I don't need to do anything to rebuild this layer. But layers like the one containing the new JRE does get rebuilt. So your Buildpacks only do the work required to build the tiny piece of your image that's changed instead of rebuilding everything naively. Rebase provides an even more performant version of this. So instead of requiring Buildpacks to rerun in containers and rebuild specific layers, if you're doing a rebase, you don't even need to start a container or build anything at all. You simply upload a new version of the OS packages to the repository and create a bunch of new application manifests that point at the new layers, and it's done. So what used to be the most expensive type of update in a Docker file, updating the base image, is now the cheapest. You don't even need to start a container or rebuild anything. Finally, layered digests are reproducible. So unlike what happens by default in a Docker file, Cloud Native Buildpacks is going to zero out the timestamps in all of the files, in all of the layers in your image. So two layers that contain the same content are going to have the exact same digest. And what that means is layers can be reused. This happens between rebuilds of a given image. So you can see this is the export that came from our previous JRE change example. All of the layers that I didn't need to rebuild can be reused directly out of the registry, and only layers that have changed even need to be uploaded to the registry at all. I can directly reuse blobs that already exist on the registry. So the amount of data transfer required from this is exactly the size of my JRE and one configurer that depends on the JRE version. So I only need to upload the JRE, and instead of requiring storage space equal to an entire second copy of my image, it's only the new layers that are taking up more space in my registry now. So we've talked about this in terms of Buildpack-provided layers like the JRE, but this can even apply to the app layer itself. Buildpacks can subdivide the app into layers using slices. So what they should do is group files that are likely to change in tandem into an application slice. And this allows for substantial layer reuse even when some application files have changed. So if I push a new version of my source code and one file has changed, rather than rebuilding the whole app and that being an entirely new layer in size equal to the application itself, because I've subdivided, a build pack has subdivided the application into 5 individual layers here. It's only the layer that contains the changed file that needs to be updated, and all of the others can be reused. So this is very powerful because, again, it minimizes data transfer, it minimizes storage space that you're using in the registry. And because these layers are reproducible, it actually allows for layer reuse between images. So if I have 2 slightly different versions of an application, if I can isolate the parts that are different because they're semantically linked into one layer, but 90% of it is the same, they can actually share those layers without having to upload. You don't have to store a new version of the entire application for each version of the image. Finally, let's talk about data transfer. So how a lot of this works, before we're talking about Buildpacks choosing to rebuild particular layers because only that layer has changed. You might have been asking yourself, how does a Buildpack know that something in that layer is supposed to have changed? What happens is metadata from the previous image is restored to disk before the Buildpacks run. And then the Buildpacks can use this metadata to decide whether to rebuild the image or not. Another feature that's provided to Buildpacks is the option to create a cached layer. So if a layer is cached, in addition to restoring the metadata for that layer, the entire layer itself will get restored. This is really beneficial if the contents of the previous layer are either necessary at build time or are advantageous for creating the new layer. So if I had a layer that contained node modules, that's something that I'd want to cache, because if an update to my app added a single additional module, having the previous version of the node modules will make that operation much faster. Something like a JRE, having that present locally does not make a new build of that layer faster, right? If I want to go from one patch version of a JRE to another, having the previous version on disk does not speed up anything. So for that reason, launch layers never flow backwards. If a layer is not cached, like the JRE in most examples, it will never get restored to disk during a rebuild. Instead, Buildpacks can, by leaving the metadata file and not providing any changes, indicate that the layer that exists in the registry now should be reused as is. So you can very powerfully reuse layers from previous images based on their metadata without ever having to download the layer locally. Layers that are restored are generally not restored from the previous image. They're restored from a cache. Because some layers are not actually exported into the image, they're build-only layers, so keeping them in a separate cache is valuable. And the lifecycle provides 2 methods of caching, either in a volume or in an image, which have different advantages in terms of speed in different environments and also in terms of availability. Finally, I keep saying finally, it's not finally yet, guys. There's gonna be a little bit more. Another way we minimize data transfer is using something called run image mirrors. So right now I'm looking at a data that's describing a builder image. I'm using Pack to print this data, and the data is being scraped from one of the labels we talked about earlier. And as we mentioned earlier, run image is used as the base image when creating an app image. So it might be confusing at first to see that there are 2 run images here. So the question becomes, when I create my app image, which of these images is it going to use? And what's actually happening is that these images should be identical, and this builder is providing 2 different mirrors. So if I'm using this builder and I'm exporting to GCR or I'm exporting to Docker Hub, the lifecycle is going to choose the best mirror from the set of options that are available and therefore minimize data transfer. So as long as there's a mirror on my target registry, I don't need to copy over the entire run image onto the new registry. I can use a registry feature called cross-repo blob mounting to use the layers in the run image that exist on the registry already without having to upload anything. So this can, especially for images that use large base images with a lot of dependencies, this significantly cuts back on the time in a build against a registry. So we've talked a lot about data transfer, and the natural way to think about data transfer is when you're pushing an image to a registry, like how much data you need to upload. But it's important to remember that data transfer matters at runtime as well. So if I'm running in Kubernetes on one of these nodes, 100 different Java apps, let's say it's a big node. If I've built all these Java apps with Dockerfiles, even if they all contain the exact same JRE, the timestamps on those files are going to be different. So this node, when it's pulling those images, doesn't know that those layers are the same because they have different digest. So every time I start one of these apps on these nodes, I need to download the entire image again, including large dependencies like the JRE. And I'm going to be maintaining 100 different copies of what's essentially the same thing. But if you're using Cloud Native Buildpacks, so you therefore have totally reproducible layers, a layer that's containing a particular version of the JRE is going to be one that's produced by the same build pack. It's going to be identical every time. Therefore, if I'm starting a new Java app and a different Java app on this node is already using that layer, I don't need to wait to re-download it again, which can significantly improve start time. And I don't need to store another version of that layer on my node, which can improve disk usage on my node. So finally, we're going to talk about portability. Part of this, a lot of the portability benefits are in contrast to previous build packs, which were deeply tied to the platform that ran them. And therefore, although they provided a lot of these benefits, couldn't be used in as many situations. But now that we've embraced OCI standards with this next generation of build packs, the image that you create using Pack can be run in Kubernetes, can be run in Docker. Same is true with images produced by any of the platforms. So you can really build once and run anywhere, which is powerful and different than the platform-specific build technology represented by the previous iteration of build packs. In addition to that, we've made changes recently to further embrace the OCI standards. So try to expose build pack concepts through the through primitives that make sense when you're running an OCI image. So inside our image, we have something called the launcher, which can launch different process types. And you can configure which process type it launches by setting it as the entry point. So this is intuitive because the entry point is generally the application that an image would be running so that users can provide additional arguments using the command. So now that we've mapped process types onto the entry point, you can use this same primitive to toggle between different CMB processes in an interface that is familiar if you're used to using vanilla Docker images, but still provides Buildpack powered features. So processes that were provided by Buildpacks that run profile scripts before launching, that set specific environment variables, stuff like that. And you can then provide additional arguments to your process, provided that your process is built to accept additional arguments. So we can create an interface that when the app image is created, a user can run just like any normal Docker image while still getting access to Cloud Native Buildpack features. An additional standard, so we've embraced the existing standards like the OCI standard, both the image standard, and we've done a lot of work against the registry specification. We have along the way found some areas where we felt like a standard was missing that we needed. One of those is a mechanism for connecting to external services. So we originally started, because we felt like we needed the standard and it didn't exist, by creating a binding specification in the Cloud Native Buildpacks project that would describe how credentials to connect to external service would be provided to an application, either at build or runtime. And then because other people were running into the same problem and we were socializing the solution, we were able to collaborate with other organizations to move this out of the Cloud Native Buildpack project, because this isn't really a build feature, and into a new Kate service binding specification, which is starting to get starting to be ready to see the light of day soon. So we're very committed to using open standards, and when we find areas where we wish there was an open standard, but it's not an area that should belong to us, try to collaborate and move that standard out of the project. Finally, so we've talked a lot about like high-level ideas about why Cloud Native Buildpacks can be advantageous compared to Dockerfiles, but it's worth noting that there are some things that are just straightforwardly hard with Dockerfiles. And one of them is Windows images. So this is something that's come new to CNB this month. We can build Windows images. Dockerfiles for Windows have a bunch of quirks, and a lot of Windows developers aren't as familiar with Dockerfiles as Linux developers are. So providing a more seamless pack build experience rather than forcing people to interact with this can really showcase the benefits of Cloud Native Buildpacks. Another area where it's very hard to create a valid image is when you're using Java native images. And Cloud Native Buildpacks integrations are likely to be recommended in this space by the Spring team, because creating one of these images correctly is hard. It's very difficult with a Docker file. But with Buildpacks, which can encode that more complex logic, and then platforms that can expose it with a simple, Maven plugin, this hard thing becomes easy using Cloud Native Buildpacks. So that was my why Cloud Native Buildpacks talk. I'd love to hear what questions you guys have. I hope the fact that I dug more into the why rather than the what wasn't too confusing. Thank you.
Thank you. Yeah, there's definitely a bunch of stuff that I learned there, because I've used them some, but they're still pretty new to me. So this is especially cool for me.
All right, I was still going to the wrong computer to get my Zoom check. This is what happens when you have so many computers. Classic Bob. Anyway, thank you so much, Emily. That was amazing. And I know in particular Java Grunt was super happy to have all that going out there. He's one of our everyday watchers, every Tuesday watchers. You might know him as Deshaun Carter out there. So anyway, how did it feel? You feel good?
Yeah, felt good. I was worried that about filling up all the time with the advantages of Cloud Native Buildpacks, but I feel like it more than did that.
Yeah, and then some. It was great. Yeah, it's just nice to not only hear like the different use cases, the different platforms it can run on, and just the ways that it's all about trying to make people's lives easier, particularly on the enterprise side. It's like stop making life difficult. Let's just do the right thing, make it the easy thing. Let's do that. So yeah, awesome. Paul, it looks like it's sunset over there for you.
Oh no, is it?
Not quite yet.
Wait, doing me?
I don't know if your room got I'm not near my lamp anymore because I had to move my laptop, but it just looks like the front of you looks kind of perfectly like the back of your backdrop. It actually looks really well.
I guess
so. Congratulations.
Thank you. It's what
Battery just got sunburned.
Yeah, right. Did you just get
am I just really like red or something?
You're a little pink.
Well, I don't know. Yeah, yeah. It's like a dusk hue.
Boom.
There it is. Hey, that's better. It's not. It wasn't worse. It just was a thing. But anyway, well, yes. Let me see if we have any questions that showed up.
Yeah, I didn't see any pop up.
Yeah, there were some streaming issues on our end that had nothing to do with you, which is funny because didn't we start our whole me asking you to be on because where you lived had streaming issues?
Yeah, my New York internet was going in and out randomly.
Yeah. So yeah, I finally connected to the hard line. So got the hard line. So that's my matrix line for you. But yeah, I'm finally on the hard line. So that's why I had to move my computer. I don't have my lamp in front of me. But the nice thing is it seems like everybody was still able to hear everything you said. So no issues there. So are you excited for next week? Are you ready for Spring 1? 2 days of fury?
Yeah. It'll be interesting to see what it's like virtual compared to in person. But I think everyone's committed to making it really great. So I'm looking forward to it.
Yeah, I mean, I know our numbers are up there, and we're excited about that. Obviously, we're going to be able to fit more people virtually than we would in like a building. That like last year, I think we had like 4,000 people. So I know we have more than that already signed up. So that's a cool thing to be able to kind of broaden our scope and get more people there. And yeah, next week with the Tasha Eisenberg, first time in front of the camera. She's excited. She's never been on this side of the things. So. She's one of the main curators of all 5 tracks. And so we're just excited to have her kind of drop knowledge on what she's looking forward to seeing, experiencing the next in the 2 days for spring 1. So that'll be next week's. Definitely show up for that. If you couldn't catch the beginning of this, Java or anybody else, you can always check. I think by tomorrow, this episode will be on our Tanzu.tv. I haven't said this before, and I've been meaning to say it for like months. If you haven't subscribed to our channel yet, subscribe to our channel. Do that. That's a thing. I know I've subscribed, and so I always get an email saying, "Hey, Tanzu," or VMware Tanzu is live, and we have a lot more content that's coming onto this actual channel.
Yeah, we actually
speak about that briefly.
We actually have some new stuff starting up as soon as tomorrow. So we have, I think, Josh Long will be on tomorrow doing some live coding, and so we're starting up a show that we're tentatively calling code. So if you go to tanzu.tv/code, it'll take you to the show page, which doesn't have a lot of detail yet, but we are kicking off with Josh tomorrow at, I think, same time, 1:00 Pacific. No.
Tiffany's shaking her head. Shake them off.
12 o'clock Pacific. All right. So there'll be some lunchtime entertainment. And then I think the following week, who's on the following week? I should have looked it up before I started.
I was going to say, do we dare even?
We only have next week.
It shouldn't even be on there because next week is Spring 1. Like everybody should be all hands on Spring 1.
That's right. Well, in that case, maybe nothing next week, but definitely Josh tomorrow. And then I've actually been doing a stream on Thursday afternoons with my friend JJ at IBM. We sort of do a co-stream. So it actually streams on both the Tanzu stream as well as the IBM stream.
Ooh.
Look at that.
Pretty special. And then on Friday, of course,
holding hands.
On Friday, we have TGIK, which I believe Duffy is actually going to be doing how we film TGIK. So they'll be going through some of the tooling like OBS and stuff that we all use to actually make these videos end up on the Twitch or the YouTube. So if you're interested in how it works, Bob, you should probably watch it. You might learn a thing or two.
I should probably.
That'll be a very interesting one. So
I'll make a note.
Hit that up. And that is now, you can do tgok.io, I think will take you there. Yep. But also it is now up on the Tanzu TV website as well. So if you go to Tanzu TV/TGIK. And we actually also now have shortcuts enabled on the website. So if you know a specific show, you can just do tanzu.tv in the show name. And if you even know the episode number, you could do tanzu.tv/12 or whatever the appropriate /Tuesday/12 or whatever the appropriate thing is. So we're slowly making things better.
Hey, look at that. That's great. Well, good. Well, yes, that's a lot. And we'll hopefully see most of all of you next week for our Spring One preview. Emily, this was great. Thank you so much.
Yeah, thanks for coming on.
Thank you guys.
And yeah, we look forward to having you back at some point, and also, break legs next week.